Welcome to Night Cosmos Sleep. On tonight's journey, we will follow a spacecraft with no cockpit, no astronauts, and almost no fuel. It may weigh only a few grams and be smaller than the palm of your hand, yet it is being designed for one of the most ambitious voyages humanity has ever imagined, reaching a black hole beyond the solar system. The spacecraft itself would be little more than a tiny computer chip mounted at the center of an ultra-thin sail several meters wide. Cameras, sensors, processors, memory, navigation systems, and communication equipment would all have to be compressed onto a surface with almost no room for anything unnecessary. Nor would it be launched by a giant rocket. Instead, an array of many laser sources near Earth would focus their light onto the sail, allowing each photon that reflects from its surface to impart a minute push. When trillions of photons continuously strike an object of extremely low mass, that force can build into a speed no spacecraft has ever reached before. In one highly ambitious scenario, the acceleration phase would last only about 17 minutes. By the time the laser beam shuts off, the spacecraft could be traveling at nearly 100,000 kilometers per second, or roughly one-third the speed of light. It could cross the distance from Earth to the Moon in only a few seconds. Yet even that velocity would not make the journey short. If the target were about 20 light-years away, the spacecraft would still need nearly 60 years to reach it, and its signal would require another 20 years to return. Its destination would not be a planet with a surface to land on, or a star visible from afar. It would be a stellar mass black hole drifting alone through the region of space near the solar system. Current models suggest that the Milky Way may contain hundreds of millions of such black holes, yet most of them have no companion star, no bright disk of gas around them, and almost no easily detectable signal. The nearest confirmed black hole is still about 1,560 light-years from Earth, while statistical estimates suggest that an undiscovered one may lie only a few dozen light-years away. But for now, we do not know where it is. That is the paradox at the center of the entire idea. Humanity has already begun calculating the spacecraft's mass, the size of its sail, the speed it must reach, and the time required for its data to return before finding the actual target it would be sent toward. An isolated black hole does not remain still and wait for us. It moves through the Milky Way just as the Sun and other stars do, so the spacecraft could not simply aim at where the black hole is today. It would have to be directed toward where that object will be 6 or 7 decades from now. Even the slightest error at departure could cause the spacecraft to miss its target by billions of kilometers. During a journey lasting many decades, it would have to determine its own direction, inspect its own components, and handle its own failures, because a command from Earth could take years to arrive. It would also need to survive cosmic radiation and interstellar dust grains that might otherwise seem harmless. At nearly one-third the speed of light, even a tiny particle of matter could strike the spacecraft with enough energy to damage a sensor or compromise its protective structure. Even after surviving the entire voyage, the spacecraft would not be able to stop easily near the black hole. It would carry no fuel for braking, and there would be no laser system waiting on the far side to slow it down. It might be allowed only a brief flyby through the region of intense gravity, recording how light bends, how time changes, and how the signal from another probe gradually fades as it approaches the event horizon. Then all of that data would have to be transmitted back to Earth through a signal so faint that, by the time it arrived, it might be reduced to only a sparse stream of photons, hidden among the countless sources of cosmic noise. The people who design the spacecraft may no longer be alive when it reaches its destination. Those who witness the launch may not be the same people who receive its final signal. So this is not only the story of a tiny vehicle capable of extraordinary speed, it is the story of how humanity searches for an object that gives off no light, sends a fragile machine across hundreds of trillions of kilometers, and sustains a scientific promise for longer than most human lifetimes. Before that palm-sized spacecraft can begin its journey, we must return to the first question. What do we truly know about black holes, and what have we only observed from an immense distance? At the center of the Milky Way, about 26,000 light-years from Earth, lies a region of space that does not appear as a clearly defined object. No star there is bright enough to explain what is happening. Instead, Astronomers observe stars near the galactic center, racing along tight orbits at tremendous speeds, then curving back around a point that seems completely empty. One of them, the star S2, takes about 16 years to complete a single orbit. From its path, scientists have concluded that something at the center must contain roughly 4 million times the mass of the Sun, compressed into an extraordinarily small region. That object is known as Sagittarius A, the supermassive black hole at the center of the Milky Way. No one has seen the black hole itself in the way we see a planet or a star. What appears through our telescopes is only its influence on things that can still produce light. The stars reveal how strongly the surrounding space has been curved, while hot gas near the center shows matter moving through an immense gravitational field. Each orbit measured with greater precision eliminates more alternative explanations, until the most reasonable possibility remaining is a black hole hidden in the darkness. This is how humanity began to understand black holes. Not by seeing the objects directly, but by reading the traces they leave behind. A distant planet can be detected through the slight wobble of its parent star, and a black hole can be recognized by the way it pulls on stars, heats surrounding gas, or bends light. The darkest objects in the universe are discovered because everything around them no longer moves in the ordinary way. On the 14th of September 2015, humanity received an entirely different kind of trace. The two LIGO observatories in the United States detected a brief signal lasting less than a second. It did not arrive as visible light, radio waves, or X-rays. Instead, the two long arms of each detector changed in length by an amount far smaller than the diameter of a proton. That almost unimaginable shift was the signature of a ripple passing through space-time. Its source lay more than 1 billion light-years away. There, two black holes, each with tens of times the mass of the Sun, had spiraled around one another faster and faster before merging into a larger black hole. The signal crossed the universe and caused both detectors on Earth to respond in the same pattern. For the first time, humanity was not merely observing the long-term influence of black holes on nearby objects. We had heard an event in which two black holes collided, and the shape of the signal matched the predictions of general relativity with remarkable precision. 4 years later, another image brought black holes closer to the public imagination. On the 10th of April 2019, the Event Horizon Telescope released the first image of the shadow surrounding M87, the supermassive black hole at the center of the galaxy Messier 87. The image showed a glowing orange ring encircling a dark central region. It quickly became known as the first picture of a black hole, but what we were truly seeing was far more subtle. A black hole emits no light from within its event horizon. The glowing ring comes from hot plasma moving outside that boundary. Where matter is accelerated and heated, powerful gravity curves the path of light, allowing some radiation from behind the black hole to bend around it and reach the observer. The darkness at the center is not a black surface that could be touched. It is a shadow formed when many paths of light are captured or redirected away from our line of sight. The image was created by combining data from radio observatories across Earth, effectively turning the entire planet into one enormous telescope. M87 times contains billions of times the mass of the Sun, but because it lies more than 50 million light-years away, its shadow still appears extraordinarily small in the sky. The image did more than reveal a black hole. It also demonstrated the limits humanity had to overcome to observe such an object from so far away. In 2022, the Event Horizon Telescope released an image of Sagittarius A. Because the matter surrounding this black hole changes so rapidly, the final image had to be reconstructed from many possible states consistent with the observations. These achievements moved black holes from the realm of speculation into the world of measurable objects. We can track stars orbiting Sagittarius A, listen to distant black holes collide, and see the shadow created by the gravitational field of M87. Independent methods all point toward the same picture. Black holes truly exist, and their behavior has so far agreed extremely well with general relativity. But extremely good agreement does not mean every question has been answered. Most of the information we receive must still pass through the complex environment outside a black hole. Hot plasma moves chaotically. Magnetic fields are stretched and twisted, and surrounding gas continually brightens and fades. When scientists search for a minute deviation in the geometry of space-time, these fluctuations are like mist covering the face of a finely crafted clock. We can see its hands moving, but it is very difficult to determine whether they are running even slightly faster or slower than predicted. A black hole is not a hole carved out of space. It is a region where matter has collapsed strongly enough to create a boundary known as the event horizon. Outside that boundary, light can still escape if it is emitted in the right direction. But once it crosses the horizon, no signal can return to tell us what is happening on the other side. Science must therefore study black holes through the events occurring just outside that boundary. One important question is whether black holes in nature truly possess the space-time geometry described by the Kerr solution. According to general relativity, a stable black hole is essentially defined by its mass and its rate of rotation. If sufficiently precise measurements reveal some additional structure, it could be a sign that our current understanding of gravity is not the final story. Another question is whether the event horizon truly exists as a perfect boundary. Current observations are highly consistent with its presence, but we have never placed an instrument nearby to monitor how a signal changes as an object approaches it. If a probe continuously transmitted while falling toward a black hole, a distant observer would see the signal become increasingly stretched, redshifted, and faint. The way it disappeared could provide a more direct test of the nature of this boundary. A final question concerns the physical laws we use here on Earth. Near a black hole, the intense gravitational field changes the passage of time and the frequency of signals in ways predicted by relativity. But do all local laws remain completely unchanged under such extreme conditions? Observations from afar can place limits on the possibilities, while an instrument operating nearby could provide a far more direct test. None of this means that our present knowledge is unreliable. Black holes are among the most remarkable successes of modern physics. Yet as the broader picture has become clearer, the remaining questions have grown more subtle. They no longer ask whether black holes exist, but how precisely space-time behaves around them, and whether nature continues to follow familiar rules when gravity reaches its most extreme form. Answering those questions may require more than a larger telescope or a more sensitive detector on Earth. We may need to place sensors within the very region of space being studied, allowing a spacecraft to become a small laboratory flying through the gravitational field of a black hole. But before considering how such a device could be built and launched, a simpler problem remains unresolved. We need a black hole close enough that the journey would not take thousands of years. The nearest one may still be drifting through the neighborhood of the solar system, absent from every astronomical catalog. The nearest black hole humanity has confirmed does not lie beyond the solar system. It is about 1,560 light-years away, so distant that even a spacecraft traveling at 1/3 the speed of light would need thousands of years to reach it. The object is known as Gaia BH1. It does not appear as a dark point in the sky, but was identified through a sun-like star orbiting an invisible mass. The star's motion reveals that its companion weighs several times more than the Sun while emitting almost no light. Among the black holes that have been widely confirmed, Gaia BH1 remains the closest to Earth. A distance of 1,560 light-years can make it seem as though every black hole is too remote for an interstellar mission to have any practical meaning. But Gaia BH1 is only the nearest black hole we have found, not necessarily the nearest one that truly exists. A map with no marker does not always mean the land is empty. Sometimes it simply means the mapmaker has not yet had instruments sensitive enough to detect what is there. To understand why scientists believe another black hole could be much closer, we must return to the time before these objects formed. A star exists through a balance between gravity pulling matter inward and energy from its core, creating outward pressure. For most of the star's life, these two processes keep it stable, but the fuel in the core does not last forever. When a sufficiently massive star reaches the end of its life, its core may no longer generate enough pressure to resist its own weight. The core contracts rapidly. In some cases, the outer layers are blasted away while the center continues collapsing until a stellar mass black hole forms. This process has repeated across many generations of stars throughout more than 10 billion years of the Milky Way's history. Each time a star ends in this way, the galaxy gains another dark object, that may outlive nearly every source of light that once surrounded it. No one knows exactly how many stellar mass black holes are drifting through the Milky Way. The number depends on how many massive stars were born, how much material they lost, and what occurred during the moment of core collapse. NASA often uses an estimate of around 100 million black holes, while some theoretical studies place the total between 100 million and 1 billion. Whether we choose the lower or upper end of that range, the black holes we have observed still represent only a tiny fraction of the number predicted. This does not necessarily mean the models are wrong. The easiest black holes to detect usually have a companion star, because gas pulled from that star can heat up and glow before falling into the darkness. Without such a source of matter, a black hole becomes almost completely silent. It still has mass, still curves space-time, and still travels through the Milky Way, but it produces no light of its own to announce where it is. We can imagine the region around the Sun as an enormous city viewed from above. The stars are illuminated windows. An isolated black hole is like a house with all its lights turned off. It has not disappeared from the city, nor has it lost its mass. The difficulty is that, from very far away, the dark house is hard to distinguish from the empty space between the glowing windows. Gaia BH1 was found because it is not entirely alone. Its companion star acted like a lamp placed beside the dark object. When Gaia measured the star's motion with great precision, its orbit revealed an invisible mass pulling from the other side. But if a black hole has no companion star, does not pass through a sufficiently dense region of gas, and does not happen to distort the light of a distant source at exactly the time we are observing, it may remain hidden. In 2025, a study examining the possibility of sending an interstellar spacecraft to the nearest black hole attempted to estimate the target's distance using what we know about the number of black holes and the distribution of stars around the Tenti Sun. The result did not identify a specific location. Instead, it suggested that if population models are approximately correct, the nearest object might lie somewhere between 18 and 40 light-years away. A simpler estimate had previously used about 20 to 25 light-years as a favorable mission scenario. These numbers do not mean that a black hole has been observed 18 light-years away, nor do they guarantee that one will be found within 40 light-years. This is a statistical inference. If a very large number of black holes are distributed throughout the Milky Way, the likelihood increases that at least one lies relatively close to the solar system. But an average value cannot tell us whether our own neighborhood resembles the average. Imagine scattering a large number of tiny grains across a broad floor. Knowing the total number of grains and the area of the floor allows us to estimate the distance to the nearest one. But it does not tell us whether it lies to the left or the right. The region around our feet may also happen to be emptier than the rest. A distance of 18 to 40 light-years carries the same meaning. It gives us a reasonable scale for the search, but it does not give us a destination. Even if such a black hole lies at the nearer end of that estimate, it would not be a threat simply because it is called a black hole. At a distance of dozens of light-years, the gravity of a stellar mass black hole would affect Earth in the same way as any other object of equal mass at the same distance. It would not silently pull the solar system toward itself like a vacuum cleaner. Its influence would be far weaker than the gravity of the Sun and the planets around us. If the Sun were replaced by a black hole with exactly the same mass, Earth would continue moving in almost the same orbit. The catastrophe would come from losing sunlight and heat, not because the black hole would suddenly pull more strongly than a star of equal mass. What makes a black hole extraordinary only becomes important when matter comes very close to the region where its mass has been compressed into an extremely small volume. A black hole, 20 or 30 light-years away, would therefore matter, not because it threatened us, but because it could become the nearest strong-gravity laboratory humanity might ever have the chance to reach. At that distance, a sufficiently fast spacecraft would still need to travel for many decades, but the journey would no longer have to last thousands of years. The idea of placing sensors near a black hole could be discussed as an extraordinarily difficult engineering problem rather than a voyage entirely beyond human timescales. Yet no spacecraft can be launched toward a location created by statistics. A mission lasting close to a century would require the target's real coordinates, real distance, and real motion. The black hole would need to be discovered early enough for astronomers to track it over many years, determine how it moves through the Milky Way, and predict where it will be when the spacecraft arrives. This brings us back to the dark city surrounding the Sunday. If somewhere within a few dozen light years there is a house with no lights on, we cannot find it simply by looking for the brightest place. We must pay attention to how background light is distorted, how a star gently wobbles, or how a faint cloud of gas suddenly begins to glow. A black hole does not give us an image of itself, but its gravity still leaves traces on anything that passes close enough. The next problem, then, is no longer whether a nearby black hole could exist. It is how to find an object that emits no light within a sky filled with billions of other sources. An isolated black hole does not appear as a dark spot with a clearly defined outline. If there is no suitable source of light behind it and no surrounding matter being heated, a telescope may look directly through that region of space without noticing anything unusual. The black hole is still there, still carrying mass and curving space-time, yet it sends us almost no signal of its own to reveal its location. For black holes with companion stars, the search is somewhat easier. When Gaia measures a star's position over many years, it can detect a tiny, repeating motion. If no other luminous star is massive enough to produce that orbit, astronomers may begin to suspect that the unseen companion is a black hole. Gaia BH1 was identified in this way not because the black hole itself was glowing, but because the nearby star was moving around a mass that could not be seen. A truly isolated black hole, however, has no such beacon. It does not pull a star through an easily recognizable orbit, and it may drift through gas too thin to produce any significant radiation. In that case, the most important method of detection depends on something simpler. Even though a black hole emits no light, its gravity can still alter light arriving from an object behind it. Imagine a perfectly transparent magnifying glass drifting in front of a very distant lamp. We cannot see the lens itself, but when it passes through exactly the right position, the lamp's light is focused and appears brighter. A black hole can create a similar effect. When it passes close to the line of sight between Earth and a background star, the curvature of space-time redirects the star's light, causing more of it to reach the observer. The distant star temporarily brightens, even though the black hole remains completely dark. This effect is known as gravitational microlensing. The word micro does not mean the black hole is small. It means the distorted images lie too close together for telescopes to resolve them as distinct arcs of light. Astronomers usually observe only the star's brightness gradually increasing, reaching a peak, and then returning to its original level. The shape and duration of that change contain information about the dark object that passed in front of it. The required alignment is rare. For that reason, surveys cannot simply choose a dark region and wait for a black hole to appear. They must monitor enormous numbers of stars over months or years, searching for variations that match the pattern of gravitational lensing. Even when a star brightens in exactly the expected way, the object in front of it is not necessarily a black hole. White dwarfs, neutron stars, and wandering planets can produce similar effects. Events lasting several months are often more noteworthy, but their duration only helps narrow the possibilities. By itself, it does not reveal the object's mass. To go further, scientists must measure more than the star's brightness. They also track its apparent position. As the light is bent, the background star seems to shift by an extremely small amount before slowly returning to its original location. It is as though the invisible magnifying glass not only makes the lamp brighter, but also causes its image to slide slightly to one side. In 2011, 2 ground-based observing programs detected an unusually long microlensing event in the direction of the Milky Way's central bulge. The background star remained magnified for about 270 days. Hubble later tracked its position through 8 observing periods spread across 6 years. One research team concluded that the lens had a mass of about 7.1 suns and detected no light from the object itself, making it consistent with an isolated stellar mass black hole. Another team analyzed the same event and obtained a lower mass range, leaving open the possibility that the object was either a massive neutron star or a lightweight black hole. The difference illustrates just how difficult these measurements are. A small change in the model of the background star's motion, or in the motion of Earth, can significantly alter the result. Finding a candidate is therefore only the beginning of many years of observation. Earth's orbit around the Sun becomes part of the measurement as well. As our observing position changes with the seasons, the event's light curve shifts slightly. This parallax effect helps estimate distance and reduce the ambiguity between the object's mass, velocity, and location. Combining changes in brightness, apparent position, and parallax allows astronomers to come closer to determining how far away the object is and in which direction it is moving. These measurements require patience because the black hole does not repeat the event. A single alignment may last for months, but the positional shift must be tracked for years to separate the star's natural motion from the signature of the dark object. In the future, the Nancy Grace Roman Space Telescope will repeatedly observe the densely populated star fields near the center of the Milky Way. Its wide field of view and high resolution will allow it to record many more microlensing events, including long-lasting events that may be caused by stellar mass black holes. Roman will not see the black holes directly. Its advantage lies in observing enough stars that these rare alignments are less likely to pass unnoticed. Gravitational lensing is not the only path being explored. An isolated black hole can still encounter matter as it moves through the interstellar medium. If it enters a sufficiently dense cloud of gas, some of that material may be drawn inward, heated, and made to emit faint radiation. Recent models suggest that the signal could appear in infrared light, X-rays, or radio waves. But the conditions must be favorable, and so far, no radiation from an isolated black hole has been confirmed with certainty. A faint radio or X-ray source therefore cannot automatically be labeled a nearby black hole. The sky contains many kinds of objects capable of producing similar signals. To transform an unusual source into an interstellar destination, scientists would have to demonstrate that it has the appropriate mass, lacks a luminous companion star, and moves in a way consistent with an isolated object. Observations across multiple wavelengths can eliminate alternative explanations, but gravitational influence remains the most decisive evidence. Finding a black hole does not yet mean knowing how to reach it. A survey may confirm that a dark object lies within a very small region of the sky, but a spacecraft launched today would not need to meet the black hole where it is today. It would have to arrive where the black hole will be 6 or 7 decades from now, while the target, the Sun, and the spacecraft all continue moving through the Milky Way. The difference between detection and precise localization lies in this degree of accuracy. Detection is like noticing a ship on the horizon. Planning a future encounter requires knowing how far away it is and in which direction it is traveling. A small error can grow throughout the journey until the predicted meeting point and the object's actual position are separated by billions of kilometers. For this reason, once a nearby candidate is discovered, observations may need to continue for many years. Astronomers would have to track its motion relative to background stars, measure its parallax as Earth changes position, and determine whether the object is being influenced by an unseen companion. Only when its future path has been constrained with sufficient accuracy could engineers calculate a trajectory capable of reaching it. Even then, the black hole would provide no beacon for the spacecraft to lock onto. The probe would have to use the positions of stars and make extremely small course corrections to limit the accumulation of error. Its navigation system would need to operate autonomously, because every command sent from Earth would take years to arrive. The first obstacle to the mission may not be building a light sail or producing a laser beam powerful enough to propel it. Before any of that, humanity must discover a sufficiently nearby black hole, prove that it truly is a black hole, and predict its future position with a degree of precision never before required for an interstellar journey. Yet even after the final destination has been marked on the map, another limit remains unchanged. A few dozen light years may be considered very close in astronomy, but for every spacecraft that exists today, it is still a distance that would take thousands of years to cross. In astronomy, an object 20 light years from Earth can still be described as relatively nearby. That distance is very small, compared with the Milky Way's diameter of roughly 100,000 light years, but for a spacecraft built by human hands, it opens into an expanse that seems almost endless. The difference lies in how galaxies and human beings experience distance. To the galaxy, 20 light years is only a short stretch. To present-day technology, it is a journey lasting longer than hundreds of generations. A light year measures not time, but the distance light travels in 1 year, about 9.46 trillion kilometers. Light from the moon takes a little over a second to reach Earth, while sunlight takes about 8 minutes. When we look at the sun, what enters our eyes is light that left its surface 8 minutes earlier. But if a black hole lies 20 light-years away, even the fastest signal in nature must travel continuously for 20 years to reach it. There would be no way to send a command and receive a response within the same day, the same year, or even the same decade. 20 light-years is nearly 190 trillion kilometers. The number is too large to visualize directly, but we can begin to grasp it by considering the fastest spacecraft ever created. During its closest approaches to the Sun, Parker's solar probe has reached speeds of nearly 200 kilometers per second. On a human scale, that is extraordinary. It could cross the width of a country in only a few dozen seconds. Yet, even if Parker could maintain that speed along a straight path, it would still need more than 30,000 years to travel 20 light-years. The fastest object humanity has ever built becomes almost motionless when placed on an interstellar scale. This reveals that the obstacle is not simply that today's rockets are slightly slower than they need to be. The gap between the two speeds is far too great to close with a single generation of more powerful engines. A spacecraft intended to reach a target 20 light-years away in about 60 years would have to maintain nearly 1/3 the speed of light, close to 100,000 kilometers per second. Compared with Parker's solar probe, this would not be an ordinary advance, but a complete transformation in how a spacecraft is accelerated. Chemical rockets are highly effective within the solar system, but they carry a limitation that is extremely difficult to overcome. To move forward, a rocket must expel matter behind it. To gain more speed, it must carry more fuel. But fuel has mass, which means the rocket requires additional energy to accelerate the unused fuel it is still carrying. The farther and faster the mission, the smaller the share of mass available for scientific instruments becomes, while the portion devoted to fuel grows larger and larger. We can imagine the spacecraft as a traveler beginning a long journey with all of their food carried on their back. To go farther, the traveler must bring more food, but the heavier backpack makes every step more exhausting, so even more food is needed to replace the energy spent carrying such a heavy load. Eventually, most of the effort is no longer being used to reach the destination, but simply to transport what will be consumed along the way. Rockets face a similar limit, though on a vastly greater scale when their speed approaches a significant fraction of the speed of light. If chemical propulsion were used in an attempt to accelerate a spacecraft to 1/10 the speed of light, the amount of fuel required would grow beyond any practical meaning. The problem is not that we have not yet built a large enough fuel tank. It is that the fuel requirement increases far more rapidly than the construction and launch capacity of any civilization based on present-day technology. A larger rocket does not solve the difficulty because the added size increases the mass and creates another demand for even more fuel. Even if we temporarily set acceleration aside, the travel time alone reveals the scale of the challenge. If the black hole lies 20 light-years away and the spacecraft maintains 1/3 the speed of light, it would need about 60 years to arrive. If the target is 25 light-years away, the flight time rises to about 75 years. After the spacecraft completes its measurements, the data would then require another 20 to 25 years to return to Earth. The entire mission could therefore last somewhere between 80 and 100 years, even if every stage unfolded close to the most favorable calculations. This means interstellar distance creates two separate journeys. The first is the spacecraft's voyage to the black hole. The second is the return journey of the information. The spacecraft may have completed its mission long ago, while Earth continues waiting for decades to learn what happened. No communication technology can reduce that waiting period below the limit imposed by the speed of light. If the spacecraft were built in the familiar way, with a large body, multiple compartments, heavy engines, and an enormous supply of fuel, the energy required to bring it to interstellar velocity would exceed any realistic capability. The concept of a black hole mission must therefore move in the opposite direction. Rather than continuing to make the vehicle larger, researchers would have to shrink it until almost nothing remained except the parts that were absolutely essential. This miniaturization would not be intended merely to save material. Every gram removed would reduce the energy needed for acceleration. Once the spacecraft weighed only a few grams, propelling it with an external energy source would begin to become a possibility worth serious consideration. All of its sensors, processors, and communication equipment would have to be integrated onto a tiny computer chip, while the vehicle's largest structure might be nothing more than an ultra-thin sail designed to receive thrust from light. The spacecraft would then have no need to carry its main engine or an enormous supply of fuel. The energy system would remain near Earth, where it could be constructed, maintained, and supplied with power. A large laser array would focus light onto the sail, transferring momentum during the initial acceleration phase. The vehicle would carry only the lightest components required to continue its journey after the beam ended. This approach avoids part of the limitation of chemical rockets because the spacecraft does not have to carry its acceleration source throughout the voyage. But it creates a new kind of fragility. The laser beam can remain precisely focused on the sail only, while the spacecraft is still close enough. After that, the vehicle must coast freely across dozens of light years. If its direction is wrong at the beginning, it will have no large engine to correct the mistake. A tiny deviation could grow into billions of kilometers after several decades. Interstellar distance therefore demands more than extreme speed. It also requires precision that can endure across time. The spacecraft must be launched toward the place where the black hole will appear in the future, not where it is located at the present moment. Over 6 or 7 decades, every uncertainty in the target's position, velocity, and direction of motion will continue to accumulate. Even if all of these difficulties can be overcome, the spacecraft will still face an unresolved question at the end of the journey. Accelerating to 1/3 the speed of light is extraordinarily difficult, but slowing down from that speed is no easier. A vehicle carrying no fuel would have no simple way to stop and enter orbit around the black hole. The laser system near Earth would be dozens of light years behind it, while no similar device would be waiting ahead to bring it to a halt. This makes a flyby more realistic than attempting to stop. The spacecraft could pass through the region of intense gravity, collect data during a very brief interval, and then continue racing into deep space. But without the ability to remain nearby, every measurement would have to occur at exactly the right moment, with no opportunity for repetition. After a journey lasting many decades, the most important period of observation might be compressed into only a few minutes or a few hours. 20 light years, then, is more than simply a very large number. It forces humanity to abandon almost every familiar image of a spacecraft. There would be no spacious compartments, no fuel supply sufficient for the entire journey, and no possibility of returning home. There would only be an extremely small instrument, accelerated for a few minutes, and then left to travel silently for decades. To enter interstellar space on a time scale that still bears some connection to a human lifetime, we may have to leave the heaviest parts of the vehicle at home. The engine, the energy source, and most of the structure would not travel with it. What would be sent into the darkness is only the smallest possible system capable of observing, remembering, and transmitting what it sees. A spacecraft bound for a black hole may therefore be no larger than a computer chip, but to accelerate something so small to interstellar speed, humanity would need a sail light enough for light itself to carry it away. A spacecraft is usually imagined as a large machine with a metal body, extended solar panels, and an engine powerful enough to adjust its trajectory, but a vehicle bound for the nearest black hole may resemble nothing familiar. Its most important component could fit on the tip of a finger and be so light that even a gentle current of air inside a room would be enough to move it. At the center of the spacecraft would be a thin wafer, similar to the material platform used to manufacture microchips. Across that tiny surface, functions normally distributed among many compartments of a space probe would have to be compressed together. The spacecraft would need to sense its environment, record data, determine its direction of travel, and eventually transmit information back to Earth. Yet every component added would bring additional mass, and every extra gram would increase the energy required to accelerate the vehicle to interstellar speed. Miniaturizing the spacecraft, then, would involve far more than simply making everything smaller. When a device weighs only a few grams, there is almost no room for large backup systems. A failed camera could mean losing every image. A memory error could erase data that had been awaited for decades. Its low mass would allow the spacecraft to accelerate, but it would also make it more fragile than any vehicle ever sent into deep space. Even the power supply becomes a difficult question. Near Earth, sunlight could provide energy to extremely small solar cells, but as the spacecraft travels deeper into interstellar space, that light would weaken until it became almost useless. The device might have to remain dormant for most of the journey, waking only at predetermined times to check its direction and the condition of its components. All stored energy would have to support a voyage that could last longer than the lives of the people who built it. The wafer could not accelerate itself to a significant fraction of the speed of light. It would need a much larger surface to receive propulsion from an external source. Attached behind the spacecraft would therefore be an ultra-thin sail, several meters across but kept at an extremely low mass. One proposed concept describes a device weighing about 1 gram connected to a sail with an area of roughly 10 square meters. This is only an illustrative design, since the final dimensions would depend on the material, the instrument's mass, and the lighting system used to propel it. Once deployed, the sail would not resemble the fabric of a boat. It would be more like a membrane so thin that even a slight deformation could alter the direction in which light was reflected. The surface would have to spread across a wide area while maintaining its shape, like an extraordinarily lightweight mirror drifting through a vacuum. At the center of that mirror would be a spacecraft so small that, from a distance, it would almost disappear. Light can push the sail because photons carry momentum. Although they have no rest mass, each photon still transfers a tiny force when it is absorbed by or reflected from a surface. If a photon is reflected, the change in its direction allows it to transfer more momentum to the sail than it would if it were simply absorbed. A single photon produces no meaningful motion, but light always consists of an immense number of photons. When they continuously strike an extremely lightweight object, that tiny force can accumulate over time. This principle has already been demonstrated in space. In 2010, the Japan Aerospace Exploration Agency deployed IKAROS, a spacecraft that used a sail driven by pressure from sunlight. After the sail unfolded, tracking its trajectory showed that light had produced approximately 1.12 millinewtons of thrust, matching the value predicted by the research team. That force was extremely small, roughly equivalent to the weight of an object slightly heavier than 1/10 of a gram on Earth's surface. Yet it was enough to confirm that photons could genuinely alter the motion of a spacecraft in interplanetary space. IKAROS did not travel at anything close to the speed of light. It used the natural pressure of sunlight, a weak but continuous force that consumed no fuel. Over several years, that gentle acceleration produced a measurable change in velocity. What mattered was not the speed IKAROS ultimately reached, but the fact that it transformed an idea once considered highly delicate into a form of propulsion that had successfully operated in space. An interstellar journey would require a far more powerful version. Instead of relying only on sunlight, the sail would be illuminated by an extremely intense laser beam. The energy source would not travel aboard the spacecraft but would remain near Earth. In this way, the vehicle would not have to carry fuel tanks, a reactor, or a heavy engine throughout a journey lasting many decades. This is also the principle behind Breakthrough Starshot, a research program exploring whether gram-scale nanocraft could be sent to the Alpha Centauri system. The program aims to determine whether a sail, driven by a powerful beam of light, could accelerate a tiny vehicle to roughly 20% of the speed of light. At that velocity, a spacecraft could cross the approximately 4.37 light-years to Alpha Centauri in about 2 decades, rather than the tens of thousands of years required by present-day vehicles. Starshot is still focused on demonstrating the concept and developing the necessary technological foundations. It is not a mission ready for launch. No gram-scale spacecraft has yet been accelerated by lasers to 20% of the speed of light. The most important components, from sail materials to the laser system and methods of control, remain under study. For a journey to a black hole roughly 20 to 25 light-years away, traveling at 20% of the speed of light could make the voyage too long. To keep the total period from launch until the data return to Earth close to a century, the vehicle might need to approach 1/3 the speed of light. The basic architecture would remain similar to Starshot, But every additional increase in velocity would make the demands on energy, precision, and heat resistance far more severe. The first challenge lies on the surface of the sail itself. It would need to reflect most of the laser light, because any energy that was not reflected would become heat. If the sail absorbed too much, the material could overheat, deform, or vaporize before the acceleration phase was complete. With such an extremely thin membrane, even a slight change in shape could prevent the thrust from passing through the spacecraft's center as intended. The sail, therefore, could not merely be lightweight. It would also have to function as a highly efficient mirror at the laser's exact wavelength. The material would need to withstand intense light while maintaining an extremely low mass. Research into relativistic sails suggests that heat absorption requirements may be so strict that only a tiny fraction of the photons could be allowed to transfer thermal energy into the sail. This remains one of the widest gaps between a known physical principle and a vehicle capable of operating in reality. Even if the material survived, the sail would still have to maintain the correct orientation within the laser beam. If one edge received more light than the other, the membrane could begin to tilt or rotate. As the angle of reflection changed, the thrust would shift away from the required direction and alter the trajectory. Near Earth, the deviation might still be small, but across several dozen light years, it could cause the spacecraft to miss the target region by an enormous distance. Keeping the sail centered within the beam would be like balancing an extremely light object on top of a powerful jet of water, with no tether and no one directly controlling it. The sail's shape, the distribution of its mass, and the structure of the laser beam would all have to work together so that the vehicle naturally returned to a stable position after a slight displacement. If the system remained stable only under perfect conditions, it would be unlikely to survive the vibrations and unavoidable errors of the launch process. The sail would also need to deploy without tearing or wrinkling. A membrane several meters across yet extremely low in mass could not be handled like a thick, rigid solar panel. It might have to be folded into a very compact form during launch and then unfold through rotation or a minimal deployment mechanism once in space. Every crease left behind could alter the way light reflects from its surface. Icaros demonstrated that deploying a large sail in space is possible. Its sail was opened by centrifugal force as the spacecraft rotated, avoiding the need for an excessively heavy supporting frame. But an interstellar sail would be lighter, thinner, and exposed to a far more intense and concentrated beam of light. The success of Icaros is therefore an important foundation, not proof that the rest of the problem has already been solved. The wafer at the center would also have to endure extreme conditions. During acceleration, the spacecraft could experience forces far greater than those tolerated by a crewed vehicle. Electronics do not contain soft organs like the human body, but their connections, material layers, and microscopic structures could still crack if acceleration changed too rapidly. The mass would have to remain low, yet every component would need to stay firmly attached throughout the entire period of light-driven acceleration. Once the laser shut off, the sail might no longer serve as the main source of propulsion. It could be rotated, folded, or repurposed as part of the communication system. A surface larger than the wafer itself might help direct communication light back toward Earth. However, this would be useful only if the sail remained intact after decades of exposure to radiation and collisions with the interstellar environment. No device this small could ever be guaranteed to operate perfectly. A reasonable approach, then, would be not to place all hope in a single spacecraft. Because each vehicle would weigh only a few grams, many could be launched in the same direction. Some might fail during acceleration, some might encounter interstellar dust, and others might drift away from the intended trajectory, but the remaining probes could still have a chance of reaching the target. Multiple spacecraft could also observe the black hole along different flight paths. Instead of receiving a single stream of data from one location, scientists could compare how signals changed among probes passing through different regions of the gravitational field. The strength of the mission would then lie not in the durability of each individual vehicle, but in the ability of the swarm to continue functioning after some of its members had been lost. This approach would become practical only if the cost and complexity of each nanocraft were low enough for large-scale production. A spacecraft weighing only a few grams could not be built like a unique deep space probe, with every component requiring years of manual assembly. It would need to resemble a microelectronic system that could be manufactured in many nearly identical copies, after which the best-performing devices would be selected for launch. Yet, no matter how light the spacecraft became, it still could not leave Earth on its own. The pressure of sunlight that propelled Icaros was extremely weak. To accelerate a wafer to tens of thousands of kilometers per second within only a few minutes, the amount of light concentrated onto the sail would have to be vastly greater. The laser beam would need to remain stable, stay precisely aligned with a rapidly accelerating sail, and transfer energy without melting the material. The 1-gram spacecraft and its meter-scale ultra-thin sail therefore represent only one half of the idea. The other half would remain at home, a light-producing system large enough to transform the gentle force of photons into the initial push for an interstellar journey. The sail has been deployed, and the spacecraft is light enough. But to accelerate it to nearly 1/3 the speed of light, humanity would have to create a laser beam on a scale and with a degree of precision that have never existed before. The spacecraft has been carried to a position high enough above Earth for its sail to unfold in a vacuum, free from the drag of the atmosphere. The thin membrane stretches several meters across, while the device at its center weighs only a few grams. Far below, the laser system is waiting for the moment when the main beam will be fired. The journey itself will last for decades, yet it will begin with an acceleration phase lasting only about 17 minutes. When the first light reaches the sail, the spacecraft does not depart with an explosion, nor does it leave a trail of fire behind. Photons reflect from the surface, transferring part of their momentum before changing direction. The force produced by each individual photon is almost impossible to feel. But when a concentrated stream of light strikes an extremely lightweight object, those tiny effects continually add together. The spacecraft begins to accelerate without carrying fuel to burn aboard the vehicle itself. The light that drives the spacecraft may not come from a single emitter. A laser powerful enough for the entire mission would be extremely difficult to build, control, and cool, so the concepts being studied usually rely on an array of many smaller elements. Each one would produce only a portion of the total energy, but if they were synchronized with great precision, their light waves could combine into a single beam focused on the sail above Earth. This would be far more complex than simply pointing many lights toward the same location. Light behaves as a wave, so the timing of every element would have to be controlled with extraordinary accuracy. If part of the laser array fell out of phase, light from the different sources might not combine as intended. The beam would lose focus, reducing the thrust or causing one region of the sail to receive more energy than the others. During the first few seconds, the spacecraft would still be close enough for the system to track its position with high precision, but its velocity would continue to increase, causing the point toward which the laser must be aimed to change more rapidly with time. The system could not simply target where the sail appeared to be. It would have to predict where the sail would be when the light reached it. Near the end of the acceleration phase, control would depend increasingly on the trajectory calculated in advance, because every form of feedback would become slower relative to the spacecraft's motion. In the ambitious scenario proposed for a journey to the nearest black hole, the spacecraft could reach nearly 100,000 kilometers per second after about 17 minutes. That is close to 1/3 the speed of light, but no laser system currently exists that could perform such a launch. For now, this remains a target used to imagine the scale of technology required, not a capability that has been demonstrated in space. If the velocity increased at a relatively steady rate over that period, the spacecraft would experience an average acceleration more than 10,000 times the gravitational acceleration at Earth's surface. No astronaut could survive such conditions, because the body's soft organs and circulatory system could not endure forces of that magnitude for so long. But the spacecraft would carry no human beings, contain no pressurized cabin, and require no protection for a living body. A small microchip could withstand far greater acceleration if the force were distributed evenly and the structure contained no serious weaknesses. Even so, its small size would not make the acceleration harmless. The layers of material inside the chip might respond differently under stress, while the connection between the device and the sail would have to transmit the entire propulsive force without separating. A microscopic crack could grow during acceleration, disconnecting a sensor or pulling the sail away from its balanced position. The vehicle would have to be rigid enough to preserve its shape while remaining light enough for the beam to accelerate it to the required speed. As the spacecraft continued to accelerate, heat would become one of the greatest obstacles. The sail would be designed to reflect the laser light, but no practical material can reflect every photon perfectly. Some of the energy would still be absorbed and converted into heat. In a vacuum, there would be no passing air to cool the surface, so the sail could release heat only by radiating it into space. The intensity of light required for an interstellar flight would be so great that even a very small absorption rate could cause the temperature to rise rapidly. As the material heated, its reflectivity might change, causing it to absorb more light and produce even more heat. This process could amplify itself until the sail deformed or vaporized. The surface would therefore need not only to reflect efficiently, but also to radiate heat effectively at wavelengths different from that of the laser beam. A suitable optical structure could strongly reflect the wavelength used for propulsion while allowing thermal energy to escape as infrared radiation. This balance would have to be maintained throughout the entire acceleration phase. If even one small region became hotter than the rest, the material could bend slightly, changing the angle of reflection and causing the thrust to move away from the vehicle's center. Even a grain of dust resting on the sail could become a problem. Dust generally absorbs light more strongly than the reflective surface around it, allowing it to create a localized hotspot. Heat from that point could spread into the neighboring material and alter its optical properties. Without sufficient control, a tiny imperfection could cause severe damage before the spacecraft completed its 17 minutes of acceleration. As the velocity increased, the wavelength of the light received by the sail in its own frame of reference would also change because of the Doppler effect. The material could not be highly reflective at only one fixed wavelength, because the conditions it experienced near the end of acceleration would not be exactly the same as those at the beginning. Its reflectivity would have to remain effective across a broad enough range to prevent the temperature from rising suddenly as the spacecraft approached its target speed. While the sail struggled against heat, the laser system would have to prevent the beam from spreading too quickly. Light always expands through diffraction, so the farther it travels, the wider the focus spot becomes. A larger transmitting array would help the beam remain narrow over a greater distance, but it could not prevent the spreading entirely. As the spacecraft moved farther away, an increasing portion of the energy might spill beyond the edges of the sail, instead of continuing to produce thrust. If the laser system were located on the ground, Earth's atmosphere would become part of the problem. The air is not perfectly uniform, but constantly changes with temperature, density, and moisture. These variations distort the path of light, just as they make stars appear to twinkle when seen from the ground. For a laser beam that must remain focused on a sail only a few meters wide, even a small distortion could direct part of the energy away from the target. Adaptive optics could measure atmospheric distortion and adjust the elements of the laser array to compensate for it. However, the high-powered beam itself could heat the air along its path, producing additional turbulence that the system would then have to correct. Meanwhile, Earth would continue rotating, and the relative position of the laser array through when the spacecraft would keep changing, turning beam stability into a process of constant adjustment. Placing the laser system in space could eliminate most atmospheric effects and allow the light to travel through a more stable environment. But this approach would require launching a vast amount of equipment, power-generating infrastructure, and cooling systems into orbit. A ground-based array could connect to existing infrastructure and be repaired when necessary, while a system in space would be far more difficult to assemble and maintain. The best location for the propulsion source therefore remains a question without a single clear answer. Wherever the system was placed, the laser beam would have to keep the sail near its center throughout the acceleration phase. If one side of the sail received more light than the other, the vehicle could tilt and begin to rotate. As the surface angle changed, the direction of reflection would also shift, producing torque that could make the deviation grow even larger. Without a stabilizing mechanism, the sail could slide entirely out of the beam after only a tiny initial error. Some designs now being studied attempt to shape the sail and the laser beam so that the vehicle naturally returns to equilibrium. If the sail moves away from the center, the distribution of light would need to create a force that draws it back rather than pushing it farther away. A gentle rotation might also help spread imperfections more evenly across the surface. However, these principles have so far been tested mainly through models and small-scale experiments. They have never been applied to an object accelerating to a significant fraction of the speed of light. As the 17-minute period approached its end, keeping the energy focused on the sail would become increasingly difficult. By then, the spacecraft would be far from its starting point, while the beam would be widening and its propulsive efficiency gradually declining. Every additional second of illumination could still increase the velocity, but it would also raise the risk of overheating or losing the target. The system would have to stop at precisely the right moment when the spacecraft had reached the required speed, but the sail remained intact, and its trajectory was still within acceptable limits. When the laser stopped, photon pressure would no longer act on the sail. The spacecraft would not experience a sudden jolt like a rocket when its engine shuts down. It would simply transition from being actively propelled to moving freely through space. The velocity accumulated over those few minutes would continue carrying it away from Earth, while the immense energy source that had accelerated it remained far behind. If everything proceeded as planned, a phase lasting less than 20 minutes would have accelerated the spacecraft to nearly 1/3 the speed of light. Yet, within that brief interval, its direction and final velocity would also have been determined for the many decades ahead. Any small remaining deviation would continue to grow throughout the journey, while the spacecraft would carry no powerful engine capable of turning back or correcting a serious error. Those 17 minutes of light-driven acceleration would therefore be only the brief opening of a voyage lasting nearly a century. Once the laser beam disappeared, the spacecraft would no longer be connected to its home by an energy stream powerful enough to alter its velocity. Ahead would lie the vast space between the stars, where a device weighing only a few grams would have to keep itself functioning for 6 or 7 decades before reaching the region surrounding the black hole. When the laser beam shuts off, the spacecraft is no longer propelled by any source of energy from Earth. It continues moving with the velocity accumulated during those first 17 minutes, carrying a trajectory that has already been determined for nearly the entire remainder of the journey. If the black hole lies 20 light-years away and the spacecraft maintains a speed close to 1/3 the speed of light, the ideal voyage would last about 60 years. If the target is farther away, closer to 25 light-years, that time could increase to roughly 75 years. For most of that time, the spacecraft will not pass new planets or sweep close to brilliant stars. It will enter the vast region between star systems, where sunlight gradually fades until the sun becomes only one star among countless others. There will be no horizon against which to measure its motion, and no nearby objects to give an observer any sense of speed. Seen from the outside, the spacecraft might appear to drift silently through an almost unchanging darkness, even though it is still crossing nearly 100,000 kilometers every second. The space between the stars is often described as a vacuum, but it is not completely empty. It still contains hydrogen and helium atoms, free electrons, and extremely small grains of dust. The density of matter is so low that an ordinary spacecraft could pass through almost without noticing anything. But at a significant fraction of the speed of light, every particle encountered by the vehicle arrives with far more energy than it would in an ordinary collision. A grain of dust less than 1/1000th of a millimeter across would seem insignificant if it landed on a hand. But when it strikes a vehicle traveling at nearly 100,000 kilometers per second, it can create an intense hot spot, vaporize material, or leave a small impact crater on the surface. Studies of relativistic spacecraft suggest that interstellar gas and dust could cause erosion, carve damaged tracks through materials, and alter the outer layers of the vehicle. The severity of the damage would depend on the spacecraft's speed, orientation, protective materials, and the true density of the environment along its path, which cannot be fully known before departure. Breakthrough Starshot has estimated that during the shorter journey to Alpha Centauri, every square centimeter on the front of the spacecraft could experience around 1,000 collisions with dust grains, measuring 0.1 micrometers or larger. The probability of encountering larger particles falls rapidly, but it cannot be considered zero. A journey to a black hole could be many times longer, allowing even small risks to accumulate over several decades. The simplest way to resist impacts would be to place a thick shield at the front, but every additional layer of material would increase the mass and make it more difficult for the spacecraft to reach the required velocity. If the shield were too thin, it might erode before the journey ended. If it were too thick, the laser system would need to provide more energy during launch and might fail to accelerate the vehicle to nearly 1/3 the speed of light. The protective structure may therefore need to use lightweight, heat-resistant materials and be arranged so that the cross-sectional area facing the direction of travel is as small as possible. The spacecraft could also travel with its thinnest edge facing forward, like the point of a needle passing through the interstellar medium, instead of leaving the entire sail exposed to incoming dust. Once the acceleration phase ended, the sail might be folded, rotated behind the vehicle, or positioned in a way that reduced the impact area. However, the sail might still be needed for orientation and communication near the target, so it could not simply be discarded without considering the final phase of the mission. Keeping a structure several meters wide intact for 6 or 7 decades remains one of the challenges that Starshot has openly acknowledged does not yet have a complete solution. Along with direct collisions, the spacecraft would be continuously exposed to cosmic radiation. High-energy particles could penetrate its electronic materials, change the state of a transistor, or flip a bit in memory. A single small error might be corrected if the system detected it in time, but many errors accumulating over several decades could damage the control software, corrupt stored data, or cause an entire component to stop working. NASA has long recognized radiation as a force capable of degrading and even disabling spacecraft electronics, including during missions far shorter than an interstellar voyage. A vehicle weighing only a few grams could not surround its microchip with a thick layer of lead-like equipment inside a laboratory. A more practical form of protection might have to be built into the electronics themselves. Critical data could be stored in multiple copies across separate memory regions. Calculations could be repeated to identify abnormal results, and essential functions could be divided among several circuits operating in parallel. If one section developed a fault, the system could rely on the others to determine the correct state and restart itself in a safe configuration. But self-correction would be useful only if the spacecraft still had enough energy to perform it. During the early years, the sun would remain relatively bright, but the amount of sunlight received would decrease with the square of the distance. At 10 times the distance, the solar energy falling on the same area would be reduced to about 1%. Once the spacecraft traveled far beyond the solar system, tiny solar cells on the wafer would be almost incapable of supplying enough electricity for a device that needed to remain continuously active. A very small radioisotope source is often proposed as a possible way to provide low power over a long period, because radioactive decay proceeds steadily and does not depend on external light. Breakthrough Starshot has previously allocated part of its hypothetical mass budget to an energy source such as plutonium-238 or americium-241, but creating a complete system weighing only a few hundred milligrams remains an unsolved problem. The radioisotope power sources currently operating aboard NASA spacecraft can provide electricity for decades, but they are far larger and heavier than the total mass permitted for a nanocraft. Because power would be so limited, the spacecraft could not keep all of its sensors running throughout the entire 60-year journey. For most of the voyage, it might have to enter a deep sleep state, with only a clock circuit and a minimal monitoring system remaining active. After several months or years, it could wake briefly, check its energy level, compare the positions of the stars, and confirm that its memory remained intact. If it detected no problem, it would shut down most of its systems once again and continue its silent journey. Long periods of dormancy would conserve power, but they would also create another risk. If the component responsible for waking the spacecraft failed, the entire vehicle could continue traveling without ever becoming active again. The wake-up signal might therefore be generated by several independent clocks, or the spacecraft could restart automatically when its sensors detected a clear change in the surrounding environment. These approaches would improve reliability, but every additional circuit would consume more space, energy, and mass resources the vehicle would have almost none of. Whenever it awakened, The spacecraft would have to determine its location without relying on GPS or transmitters near Earth. It could observe the relative positions of bright stars, compare them with a map stored before launch, and then recalculate its direction of motion. Some stars have their own proper motion, while others change in brightness, so the map could not be a fixed photograph of the sky. The spacecraft would need to know how the sky was expected to change over many decades and recognize familiar patterns from a position increasingly distant from the solar system. Small course corrections could be produced with low-power photon sources, allowing the spacecraft to emit light in one direction and receive a very slight push in the opposite direction. This force would not be enough to correct a major deviation, but if applied early and precisely, it could prevent a minor error from growing into a separation of billions of kilometers. Because energy would be limited, every correction would have to be calculated carefully. The spacecraft could not continually alter its trajectory and would need to preserve most of its resources for the approach to the black hole and the transmission of data afterward. Earth might continue sending updated information about the target's position during the early years, but the communication delay would increase by 1 year for every light year the spacecraft traveled. Once the vehicle was 10 light-years away, a command transmitted from mission control would take 10 years to arrive. Even if the spacecraft responded immediately, Earth would still have to wait another 10 years to learn whether the command had been carried out successfully. A simple exchange would then take 2 decades. The spacecraft could therefore not be controlled like a vehicle on Mars, where signals are delayed by only a few minutes. Urgent decisions would have to be made locally by systems programmed before launch. It would need to distinguish a failed sensor from a genuine environmental change, select the most reliable copy of stored data, and decide when to use its reserve power. Autonomy would not be an optional feature, but a requirement for the vehicle to remain functional when it reached its destination. That autonomy would not mean the spacecraft had to think in the way a human does. Most decisions could follow strict rules tested against many scenarios before launch. Yet no one could predict every failure that might occur over 60 years. The system would need enough flexibility to recognize conditions never encountered during testing without responding in a way that destroyed the vehicle's remaining ability to operate. A single spacecraft would be highly vulnerable to the many risks accumulating throughout the journey. If a dust grain destroyed the main processor or a radiation error erased the control program, decades of waiting could end without any data returning to Earth. Because each vehicle would weigh only a few grams, a reasonable solution would be to launch many of them along slightly different trajectories, ensuring that the survival of the entire mission did not depend on a single device. The spacecraft would not necessarily need to travel close together like a flock of birds. If they flew too near one another, the same region of dust could damage several of them. Greater separation between their trajectories would distribute the risk, while different approach angles would allow them to observe the black hole from multiple positions. Some vehicles might carry sensors optimized for measuring the gravitational field, while others could preserve more energy for communication, or serve as receivers for signals transmitted by probes passing closer to the target. The concept of groups of spacecraft coordinating autonomously has already begun to be tested near Earth, though it remains far from the demands of an interstellar journey. NASA used 4 CubeSats in the Starlink mission to test relative navigation, shared observations, and coordinated operations without continuous control from the ground. This success demonstrated that multiple small spacecraft could support one another, but Starlink operated in Earth orbit and its vehicles had far greater size and resources than nanocraft. It cannot yet be considered proof that a swarm of gram-scale spacecraft could function for many decades. As the spacecraft continued onward, time on Earth would pass at its familiar pace. Engineers who were young on launch day would enter middle age and eventually retire. The computers used to design the vehicle would become obsolete, the original data formats might fall out of use, and the Mission Control Center would have to be rebuilt many times. Sustaining the journey would therefore require more than keeping the onboard hardware alive. Humanity would also have to preserve knowledge of the mission across generations. New teams would need to understand why decisions had been made many decades earlier, how to decode the signals, and what to do when the spacecraft finally communicated again. The mission could not depend on the memory of one person or a single laboratory. All documentation, software, and analytical methods would have to be transferred to new systems without losing their original meaning. If society's interest faded, the spacecraft might still reach the black hole, only to find that no one remained prepared to listen. For the vehicle itself, 60 years would contain no clear seasons or passing days. Most of the journey would consist of long periods of sleep interrupted by a few brief inspections. The sun would gradually shrink behind it, while the target ahead would still not appear as a dark sphere waiting to be seen. The black hole would emit no light for the camera to follow, so the first sign of approach might be nothing more than extremely small changes in the apparent positions of background stars. As the spacecraft entered a region where the black hole's gravitational influence became measurable, light from stars behind it might begin bending differently from what had been predicted. The vehicle's trajectory would also start to deviate slightly from a straight path under the pull of the target's gravity. After decades in which almost nothing seemed to change, those minute departures would signal that the journey had entered its final stage. The black hole would still not appear as a dark object waiting ahead. It would reveal itself only gradually, through the way the surrounding space shifted the stars and drew the spacecraft away from its original path. The tiny vehicle would have survived decades of dust, radiation, and prolonged sleep, but its greatest challenge would still lie ahead. It would be approaching the target at nearly 1/3 the speed of light, and no system would be waiting at the end of the journey to help it slow down. After 6 or 7 decades crossing the space between the stars, the spacecraft finally enters the region surrounding its target. The black hole still does not appear as a dark sphere visible to the eye. Its presence is first detected through very subtle changes. The spacecraft's path begins to curve away from its predicted trajectory. Light from background stars is deflected, and the onboard clock gradually records the influence of a stronger gravitational field. Yet, even as these signs become increasingly clear, the vehicle is still racing forward at nearly 100,000 kilometers per second. The speed that allowed the spacecraft to cross 20 light-years in about 60 years now becomes its greatest obstacle. The acceleration phase lasted less than 20 minutes, but no equivalent system is waiting at the end of the journey to slow the vehicle down. The laser array remains near Earth, hundreds of trillions of kilometers behind, while the spacecraft carries nowhere near enough fuel to brake from almost 1/3 the speed of light. Reaching interstellar velocity solves only the first half of the problem. To remain near the black hole, the vehicle would have to shed most of the kinetic energy it had accumulated. Using rockets to decelerate would require so much fuel that the initial mass would rise dramatically, making it far more difficult for the sail to reach its target speed. The entire advantage of a gram-scale spacecraft comes from leaving its energy source at home, so carrying a large braking system would return the design to the very limitation that the light sail was intended to avoid. In the most favorable scenario, a mothership might slow down, enter a stable orbit, and then release smaller probes into the region of strong gravity. Remaining near the target would provide many more opportunities for observation. The instruments could monitor multiple orbits, repeat measurements when an unusual signal appeared, and compare data over an extended period. A study published in May 2026 examined the possibility of using probes in orbit around a black hole, but it had to assume from the beginning that the spacecraft had already found a way to decelerate and enter the required orbits. The authors themselves acknowledged that the problem of slowing the vehicle still lacked a convincing engineering solution. Even if deceleration could be solved, the mothership could not safely approach the event horizon with a sail several meters wide. The gravitational field around a stellar mass black hole changes very rapidly with distance. The section of the sail closer to the black hole would experience a stronger pull than the section farther away, creating tidal forces that could stretch or destroy the structure. Smaller probes, no longer burdened by an interstellar sail or antenna, could travel deeper, but they would have to continue transmitting data to the mothership before the communication link became too weak or was cut off entirely. If the spacecraft cannot be slowed, the more realistic option is to accept that the encounter must take place in motion. The vehicle would sweep past the black hole, gather data along the way, and then continue outward on the far side. In July 2026, a follow-up study focused specifically on the possibility of using flyby probes that would not need to decelerate. The idea was still described as extraordinarily difficult and speculative, but removing the requirement to enter orbit avoids the greatest energy obstacle at the end of the voyage. A flyby would not mean simply passing the black hole and taking a few photographs. To collect meaningful data, the formation would have to be prepared in advance so that each probe traveled through the gravitational region along a different direction and at a different distance. The mothership, carrying the large sail and the communication equipment needed to reach Earth, would remain at a safer distance. Shortly before the closest approach, it could release multiple probes weighing less than a gram and measuring under a centimeter across, allowing them to move nearer to the target while experiencing fewer tidal stresses across their structures. The navigation demands during this phase would be more severe than at any earlier point in the mission. The distance from the solar system to the target might be nearly 200 trillion kilometers, yet the region where the strongest gravitational effects become clear would be extremely small compared with the interstellar journey. Around a stellar mass black hole, trajectories near the event horizon are often calculated on scales of tens to hundreds of kilometers, depending on the object's mass and rotation. After traveling for decades through an immense expanse of space, the spacecraft would have to enter that narrow region with an error small enough to keep the probes from passing too far away, while also preventing them from entering the dangerous zone earlier than intended. The black hole would not remain stationary while the spacecraft was in flight. It would continue orbiting through the Milky Way, while the solar system would also change position. The trajectory would have to aim for where the target would be many decades later, not the coordinates measured on launch day. Small course corrections could limit the error, but they could not fully repair a trajectory that had already drifted too far. As the spacecraft approached the black hole, every piece of navigational data obtained from starlight, orbital curvature, and relative motion would have to be processed on board. There would be no time to wait for instructions from Earth. By then, a control signal would need 20 years or more to arrive. The spacecraft would have to recognize when the gravitational field began to produce a measurable effect on its trajectory, determine when to release the probes, and select the appropriate observing mode on its own. Decisions made within a few seconds might depend on software written many decades earlier, because by the time humanity learned what was happening, the entire encounter would have been over for years. The observing window would be almost impossibly brief. If the vehicle were still moving at nearly 100,000 kilometers per second, it would cross a region 1 million kilometers wide in only about 10 seconds, even before accounting for the way the gravitational field altered its path. The most important measurements would not continue for months, as they might from orbit. They could be compressed into only a few minutes, during which every sensor would have to operate simultaneously, with no chance to return if the first attempt failed. The cameras would not be used merely to produce striking images of the region around the black hole. Optical data would reveal how starlight was being bent, while onboard clocks recorded changes in the passage of time. Transmitters and receivers would track delays, frequency shifts, and variations in signal strength between the probes. Rather than relying on a single measurement, scientists would have to combine many subtle changes to reconstruct the shape of space-time around the central object. Diversity in the flight paths would play an especially important role. If every probe followed the same trajectory, they would collect almost the same kind of data and face many of the same risks. By separating them along slightly different paths, each device would experience the gravitational field at a different intensity. Probes passing farther away would provide stable reference points, while those approaching more closely would record stronger effects. Comparing their clocks, light transmission paths, and orbital deflections could help distinguish the black hole's true influence from errors within the instruments. Not all of the probes would need to survive. Some could pass at relatively safe distances and continue transmitting data to the mothership. Others could be sent closer, where small departures from the predictions of general relativity might become easier to detect. A final probe could travel directly toward the event horizon, transmitting continuously until its radiation became increasingly redshifted, stretched, and weakened beyond the ability of the receivers to detect it. It is important to remember that a black hole does not pull in everything nearby the way a vacuum cleaner draws in matter. At a sufficient distance, its gravity behaves like that of any other object with the same mass. A vehicle with the proper speed and direction could still pass by, have its trajectory bent, and then continue moving away. Only when a probe entered a region of unstable orbits or crossed the event horizon would the possibility of returning disappear. The path of each probe would also depend on the black hole's rotation. If the central object were spinning rapidly, the surrounding spacetime would be dragged along with that motion. A probe traveling in the direction of the rotation might follow a different trajectory from one moving against it, even if their initial approaches were nearly symmetrical. The difference would provide information about the black hole's spin and the geometry of its gravitational field, while helping determine whether the object truly matched the Kerr solution of general relativity. Moving closer would not always produce better data. The strong gravitational field would make the effects being measured more pronounced, but it would also shorten the available communication time. Signals emitted from deeper regions would be shifted toward longer wavelengths and weaken before reaching the mothership. The path of the light could bend away from the receiver, while a probe traveling too close might disappear before transmitting enough information. The ideal trajectory would have to balance the strength of the physical signal against the ability to carry the data back out. The mothership would not remain still and wait. It would continue racing through the system at tremendous speed, causing its distance from the probes to increase rapidly after the point of closest approach. During that brief interval, it would have to receive multiple streams of signals, verify that the data was complete, and store secure backup copies. The sail once used for acceleration might be repurposed as a large communication component, but only if it remained sufficiently intact after decades of exposure to dust and radiation. The smaller probes would not have enough electrical power to transmit for long. They would need to send their data almost as the measurements were being made, rather than storing it and waiting for more favorable conditions. The mothership would become the only bridge between the probes approaching the black hole and Earth. Once the distance grew beyond the communication limit, any surviving probes would continue drifting through space, but their voices would no longer reach the receiver. Compared with entering orbit, a flyby would have many limitations. Measurements could not be repeated after an anomaly was detected. A sensor failure at the critical moment could cause the data to be lost forever. There would be no opportunity to follow multiple orbits or observe how the environment changed over time. In return, however, the spacecraft would not have to solve the immediate problem of decelerating from relativistic speed. This might be the necessary compromise that makes the first close encounter feel slightly less remote. 60 years of preparation would therefore not lead to a quiet stop beside the black hole. The entire journey would end in an encounter taking place at high speed, with the mothership and its probes following paths calculated long in advance. They would not arrive to stay, they could not return, and they would have no opportunity to repeat the approach. Every piece of data would have to be collected during the brief interval before the formation spread apart and the black hole began to recede behind them. The spacecraft would not need to see inside the event horizon, because no information from within that boundary could return. By precisely measuring how trajectories were curved, how clocks changed their rhythm, and how light signals were stretched, it could ask questions deeper than any telescope observing from Earth. Those brief minutes of the flyby might reveal whether the geometry around the black hole truly matched our predictions, how the event horizon manifested itself, and how faithfully the familiar laws of physics continued to hold within an extraordinarily powerful gravitational field. After a journey lasting many decades, the spacecraft would not approach the black hole merely to photograph the darkness ahead. Its greatest value would lie in transforming the region around that object into a strong gravity laboratory, where trajectories, clock rates, and light signals all respond directly to the shape of spacetime. Those changes might be subtle, but they would be less obscured by hot gas, dust, and magnetic fields than observations made from Earth. This is why an instrument near a black hole could answer questions that even increasingly powerful telescopes still struggle to resolve conclusively. Current observations are all in strong agreement with general relativity, gravitational waves, X-ray radiation, and images of black hole shadows have allowed humanity to test gravity under increasingly extreme conditions. Yet the data must always pass through complex astronomical environments and be interpreted using models that cannot perfectly describe every motion of the plasma. A probe near the target would not eliminate every source of uncertainty, but it could replace much of that chaotic matter with signals deliberately created by humans, whose frequencies, timing, and transmission paths were known in advance. The first question concerns the true shape of space-time around the black hole. According to general relativity, a stable, rotating object with almost no electric charge is described by the Kerr solution. Its mass determines the overall strength of the gravitational field, while its rotation drags the surrounding space-time along with it. A spinning black hole therefore does more than pull objects inward. It also twists trajectories and the paths of light in the direction of its rotation. This effect could be measured more clearly by placing two instruments at different locations. The mothership would remain at a relatively safe distance, while a smaller probe traveled deeper into the gravitational region. The inner device would transmit a steady sequence of electromagnetic pulses, while the mothership recorded the arrival time, frequency, and shift of each pulse. If the geometry around the object truly followed the Kerr solution, the behavior of the signal could be predicted from the black hole's mass, spin, and the trajectories of the two devices. The actual data could then be compared with those predictions to determine how closely they matched. What matters would not be a single signal, but the entire pattern of change over time. As the probe moved, its signal could be blue shifted while it approached the mothership and shifted toward longer wavelengths as it moved away. The gravitational field would also cause time on the probe to pass at a different rate from time measured by a clock farther away. These two effects would blend together, producing a distinctive pattern of variation. If the black hole were rotating, the direction of motion relative to its spin would also remove the simple symmetry from the trajectory and the signal's travel time. Scientists would not need to observe space-time directly to determine its shape. They would only need to watch how it guided the things passing through it. Just as the shape of a current can be inferred from the paths of drifting leaves, the trajectories of probes and the paths of photons could reveal a gravitational structure invisible to the eye. If several instruments passed along different routes, each measurement would provide another perspective, helping separate the influence of mass from the influence of rotation. In detailed studies published in 2026, the initial problem was simplified by considering a non-rotating black hole in a vacuum. In that case, the standard geometry would be Schwarzschild rather than Kerr. Two probes positioned at different distances could infer the central mass from their clock rates and orbital motion. If both produced the same result, the data would be consistent with the standard geometry. If the results remained inconsistent after measurement errors had been eliminated, it could indicate that the structure around the object departed from the prediction. These simplified models are only a first step, because a real black hole would almost certainly be rotating and interacting with at least some interstellar matter. The achievable precision would depend strongly on the distance of closest approach. Far from the black hole, departures from the standard geometry would usually be small and easily confused with positioning errors or clock uncertainty. Near the innermost stable circular orbit, relativistic effects would become much more pronounced. A 2026 study estimated that a probe operating near this region for several hours could test a deformation parameter at a very small level within the model being used. However, that value came from an idealized simulation that assumed the device had already entered the correct orbit and carried a sufficiently precise clock. It does not guarantee that a real spacecraft weighing only a few grams could achieve the same sensitivity. A result consistent with Kerr would still be enormously valuable. The scientific objective would not necessarily be to prove Einstein wrong. If the geometry were confirmed in a stronger gravitational region than any ever measured directly, many alternative models would be narrowed or eliminated. Physics advances not only when something unexpected appears, but also when a theory survives a new test with greater precision than before. A deeper question lies at the event horizon. This is not a solid surface or a glowing boundary surrounding the black hole. It is the boundary of a region of space-time from which no signal can return to the outside universe. Most current evidence comes from the fact that matter falling into black hole candidates appears to lose energy without producing radiation from a collision with a surface. The most natural explanation is that the matter has crossed an event horizon, although some models of ultra-compact objects without horizons can imitate many of the signs we currently observe. To test this more directly, a probe could be sent toward the object while continuously transmitting signals to the mothership. At first, the pulses would arrive regularly and remain strong enough to detect. As the device traveled deeper into the gravitational field, each pulse would take longer to escape, while the photons would lose energy. The signal would gradually shift toward longer wavelengths and become increasingly faint at the receiver. A distant observer would not see the probe cross the event horizon in the way an object passes through a doorway. In the external coordinate description, the signals it emits would arrive more slowly, become increasingly redshifted, and gradually fade. In theory, the probe would not disappear at any finite moment from the perspective of the distant observer. In practice, however, the frequency would eventually move beyond the receiver's detectable range, or the signal would become weaker than the background noise. The final silence would not occur because the probe ceased to exist just outside the horizon, but because information from it could no longer reach the mothership in a measurable form. The way the signal weakened over time could be compared with the predictions for a Kerr or Schwarzschild black hole. If the central object possessed a physical surface located just outside the expected position of the horizon, the probe would eventually strike that surface. The sequence of signals might then end in a different pattern, or the impact could produce additional radiation. Some theoretical models without event horizons predict other behaviors as well, but there is currently no evidence that these models describe astronomical black holes better than general relativity. They serve only as alternatives for comparison, helping scientists determine what the experiment should look for. This test would be especially difficult because the transmitter would have to remain precisely aimed while the probe was falling rapidly. As it approached the region of unstable photon orbits, the path of light would become extremely sensitive to the initial angle of emission. A minute deviation could cause the signal to circle the black hole along a different path or prevent it from reaching the mothership altogether. Testing the horizon would therefore depend not only on the clocks, but also on the narrowness of the transmitted beam, the receiver's frequency, sensitivity, and the relative geometry between the two devices. The probe's final sequence of pulses would carry a meaning very different from an image. It would not allow humanity to see inside the black hole, because that is impossible. Instead, the data would reveal how light behaves as its source approaches a boundary from which there is no return. What the probe could no longer transmit would be just as important as what the mothership continued to receive. After space-time geometry and the event horizon, the third test would address an even more fundamental question. Do the local laws of physics remain unchanged near a black hole? According to general relativity and other metric theories of gravity, atomic physics inside a freely falling laboratory near a black hole should be the same as atomic physics on Earth. Gravity changes how two separated laboratories compare their clocks, but it should not cause atoms in a local environment to suddenly obey a different set of rules. Some extended theories, however, allow quantities normally regarded as constants to depend on underlying physical fields. For example, the fine structure constant, which determines the strength of electromagnetic interactions, could be linked to the value of a scalar field that changes as the gravitational environment grows stronger. This has not been observed, but it remains a possibility that can be tested. Current observational limits on variations associated with gravitational fields have not reached conditions much stronger than those at the surfaces of white dwarfs, leaving the region near a black hole almost unexplored in this way. A probe could perform the comparison using two atomic transitions that respond differently to the same constant. Each transition would produce photons with a precisely defined energy. As the signal traveled from the device near the black hole to the mothership, both spectral lines would experience gravitational redshift and Doppler effects caused by motion. If local physics remained unchanged, the two lines would shift according to the predicted relationship. Only if the ratio between them showed a deviation that could not be explained by motion or gravity would the possibility of a changing fundamental constant arise. The experiment can be imagined as taking two clocks built on different physical principles to the same location. Gravity would cause both to run more slowly when compared with a distant clock, but if their underlying physics remained unchanged, the relationship between them should not vary arbitrarily. Only if the two kinds of clocks responded differently beyond what relativity predicts would scientists have reason to suspect that something deeper was occurring. The practical precision of this measurement would still depend on what instruments could be miniaturized to fit aboard a gram-scale spacecraft. A stable atomic clock, A spectroscopic light source, a processor, and a communication system would all require energy, space, and radiation resistance. Current studies mainly identify which kinds of measurements would be scientifically valuable. They have not demonstrated that the entire instrument package could be placed aboard a nanocraft and remain operational after many decades. This, therefore, remains a conceptual experiment, intended to guide technological development rather than describe hardware that is already ready. The three questions are closely connected. Geometry asks how space-time is curved. Signals from a falling probe test the boundary beyond which escape becomes impossible. Comparing atomic transitions asks whether matter continues to obey the same laws under those extreme conditions. The results would be meaningful only if trajectories, clocks, and paths of light were analyzed together, because an error in one could create the appearance of an anomaly in another. Even if every measurement agreed with general relativity, the journey would still be entirely worthwhile. Humanity would gain a more direct test of a stellar mass black hole, performed within the strong gravitational region itself, rather than inferred only from light emitted by distant gas. If a consistent deviation appeared across several probes and several kinds of signals, it could indicate that the current description was incomplete. Both outcomes would expand our understanding, differing only in the direction physics would take next. As the mothership moved away from the target region, the probe traveling deepest would continue sending its final pulses. Their frequency would fall, the intervals between them would lengthen, and their intensity would fade until the receiver could no longer distinguish them from the background noise. The device would never return, but the disappearance of its signal would itself become a measurement. The remaining probes would continue transmitting data to the mothership for a brief time before the formation spread too far apart. The encounter with the black hole would now be over. The trajectories would have been recorded, the clock rates compared, and the final sequence of light stored in memory. Yet, the results would still be dozens of light years from Earth. The scientific value of the entire journey would be completed only when the mothership turned its communication system toward home and sent that message across interstellar space. Many decades after launch day, an observatory on Earth is still pointed toward a region of sky marked long ago. No one in the room witnessed the sail unfold or watched the spacecraft leave the solar system. They have only the predicted coordinates, the encoding pattern preserved in the data archives, and the time window in which the message might arrive. Against the background noise of the sky, the detector records a few photons appearing at intervals that are not entirely random. They are not yet enough to establish certainty, but they are also too regular to ignore. If the black hole lies 20 light-years from Earth, a spacecraft traveling at nearly one-third the speed of light would need about 60 years to reach it. The data would then require another 20 years to return. For a target around 25 light-years away, the flight could take 75 years, bringing the total mission duration close to a century. These are only estimates for technology that does not yet exist and a target that has not yet been discovered, but the communication limit cannot be shortened. Information cannot travel faster than light. Once the measurements around the black hole were complete, the mothership would have to turn its transmitter toward home. It could not aim at the position where Earth appeared at that moment, because the planet would continue moving throughout the 20 or 25 years the signal spent crossing space. The solar system would also continue orbiting the Milky Way, while the spacecraft itself moved away from the target at tremendous speed. The transmitter would have to aim toward the place where the receiving telescope would be in the future, while also compensating for the vehicle's motion and any remaining errors from the flyby. Even a well-focused laser beam would gradually spread because of diffraction. After traveling dozens of light years, most of its photons would pass through empty space without ever reaching a receiver. By the time the signal entered the solar system, the illuminated region could be far larger than Earth, while the observatory captured only a tiny fraction of the original stream of light. Those rare photons would still have to be separated from starlight, background radiation, atmospheric interference, and noise produced within the detector itself. The sail that once received the propulsive force could be repurposed for communication because its area would be much larger than the wafer and could help create a narrower transmitted beam aimed toward Earth. This possibility would remain useful only if the sail preserved its shape after decades of exposure to radiation, interstellar dust, and the encounter with the black hole. The original proposal also considered a sail measuring roughly 10 square meters as a potential antenna for the transmission home, but this remains a conceptual idea rather than a device that has already been built and tested. Electrical power aboard the spacecraft would be extremely limited, making it difficult to transmit data continuously at a high rate. The remaining energy would still have to support the clock, memory, navigation system, and transmitter. The results might be compressed into brief sequences that prioritize the condition of the spacecraft and the most important measurements, then repeated many times to improve the chance of reception. Optical communication could focus energy into a narrower beam than radio, but it would also demand extraordinary pointing accuracy. A minute angular error at the source could cause the laser to miss the entire solar system after crossing dozens of light years. Humanity has already begun to demonstrate that data can be transmitted by laser through deep space. NASA's Deep Space Optical Communications System, carried aboard the Psyche spacecraft, tested high-bandwidth optical communication beyond Earth's immediate neighborhood. On the 3rd of December 2024, DSOC transmitted data from a distance of about 494 million kilometers, and ground stations received a total of 13.6 terabits during the program. NASA reported data rates at least 10 times greater than those of advanced radio systems with comparable size and power. DSOC concluded operations on the 2nd of September 2025 after exceeding its technical objectives. DSOC used a transmitter at Table Mountain as a beacon to assist with pointing, while the 5.1-meter Hale telescope at Palomar Observatory received the signal with an ultra-sensitive photon detector. The achievement showed that information could be encoded in the timing of laser pulses and reconstructed from an extremely sparse stream of photons. However, 20 light-years is nearly 200 trillion kilometers, many orders of magnitude beyond the scale of the Psyche experiment. An interstellar spacecraft would also weigh only a few grams and could not carry a transmitter or power supply of comparable size. DSOC is a foundation, not proof that interstellar communication has been solved. The receiving system on Earth would also have to survive for as long as the mission itself. Depending on a single observatory would leave the project vulnerable to weather, background light, or technical failure. A network of large telescopes in different locations could monitor the same region of sky, compare photon arrival times, and reject signals that were not consistent across the network. The final architecture cannot yet be determined, but its sensitivity would have to be high enough to recognize a deliberate transmission pattern among countless naturally occurring photons. The detector would not hear a continuous sound. It would record isolated events, with each photon producing a tiny electrical pulse. The information would lie in the timing of their arrival. Only when enough photons appeared according to a predetermined pattern could the software distinguish the signal from random noise. Important sections would be transmitted repeatedly, while error-correcting codes would help reconstruct the message, even though most of the original light never reached the receiving telescope. The opening sequence might confirm that the vehicle had reached its target, report the condition of its instruments, and identify the time of observation before the detailed measurements followed. The deeper challenge would not lie aboard the spacecraft, but in the continuity of human civilization. A project lasting 80 to 100 years would span many generations of computers, programming languages, storage formats, and scientific institutions. The software used to encode the signal on launch day might no longer run on any machine when the data returned. The original files would have to be transferred to new systems without altering their contents, while the decoding algorithms would need to be documented clearly enough for people not yet born at the time of departure to understand how to use them. Nor could that knowledge remain stored within a single research institute. Organizations may change names, merge, or cease to exist. Scientific funding may shift toward different priorities, and the people who understood the original design would gradually leave the project. The documentation would therefore need to be copied in many places, regularly verified, and deliberately passed on. Each generation would have to preserve not only the equipment, but also the reason why that region of sky was still worth listening to after decades of silence. The people who discover a black hole near Earth may not be part of the team that launches the spacecraft. The engineers who witness those 17 minutes of acceleration will likely be elderly, or may no longer be alive by the time the vehicle reaches its destination. When the signal finally returns, the control room will belong to a generation of scientists born decades after the journey began. They will have no personal memory of the spacecraft, yet they will become the ones who fulfill the promise left behind by those who came before them. Then, on a night that seems no different from any other, the pattern begins to repeat. The photons arrive only sparsely, but the intervals between them match the opening sequence preserved across generations. A second station detects the same frequency after correcting for the delay, while a third confirms that the source lies within the expected region of the sky. No image of the black hole appears on the screen, and there is still no complete graph ready to be announced. There is only a growing correspondence that becomes increasingly difficult to explain as chance. The room does not need to erupt in celebration. Those present understand that they have received only the beginning of the message, and that the work of decoding it still lies ahead. Silence feels more fitting for the journey that produced it. The light now touching the detector left the spacecraft before many of the people in the room were born, carrying data gathered hundreds of trillions of kilometers from Earth. If the measurements fully confirm general relativity, the mission will still have succeeded. If they reveal a reliable deviation, future generations will have to search for a new explanation. Whatever the result, what returns will be more than data about a black hole. It will also prove that humanity can keep a scientific purpose alive longer than the career, memory, or lifetime of any individual. A few faint photons may form the final chapter of a journey lasting nearly a century. They will have crossed interstellar dust, passed through an intense gravitational field, and returned as a pattern of light almost too subtle to detect. Within them will be the spacecraft's trajectory, its clocks, its spectra, and the questions sent outward by an earlier generation. When the detectors confirm the first unmistakable signal pattern, the final answer will have found its way to those born to continue listening. Let us return to the spacecraft smaller than the palm of a hand from the beginning of our journey. At its center is a wafer containing sensors, processors, clocks, and a communication system. Behind it is a sail so thin that light itself can push the entire vehicle out of the solar system. During the first few minutes, a laser beam accelerates it to a speed no human-made object has ever reached. Then come decades of silence, a brief flyby past the black hole, and a faint stream of photons, beginning the long journey back to Earth. None of this violates the known laws of physics, but an enormous distance still separates what can be imagined from what can actually be built. Humanity does not yet possess a laser array powerful enough to accelerate a gram-scale spacecraft to nearly one-third the speed of light. Nor do we have a sail that is simultaneously lightweight, highly reflective, heat-resistant, and capable of maintaining its shape beneath an extraordinarily intense beam. No device weighing only a few grams has demonstrated that it can survive decades of interstellar dust, radiation, and prolonged sleep cycles. Reliably transmitting data across 20 light-years also remains far beyond every communication system currently in operation. Even so, this idea did not emerge from nothing. Its individual principles have already established the first foundations. Icaros demonstrated that photon pressure can alter the motion of a spacecraft in interplanetary space. Breakthrough Starshot is studying whether laser arrays could propel gram-scale vehicles attached to sails several meters wide. Observations from Gaia and Hubble have shown that dark objects can be detected through their influence on stellar motion or the bending of background light. DSOC has demonstrated that optical communication can transmit data across hundreds of millions of kilometers at rates higher than radio systems of comparable size and power. Each of these achievements solves only a very small part of the problem. Combining them into an interstellar voyage would require a far greater leap than improving each technology individually. The sail would have to survive the laser beam and then endure the interstellar environment. The processor would need to remain lightweight while being durable enough to correct its own errors for decades. The power source would have to be small enough to fit on the wafer, yet capable of sustaining clocks, sensors, and communications after almost a century. The receiving system on Earth would also have to survive across generations so that the final message was not missed. Even the mission duration still depends on a target that has not yet been found. If the nearest black hole lies about 20 to 25 light-years away, traveling at nearly one-third the speed of light could keep the total time from launch until the signal returned somewhere between 80 and 100 years. If the nearest object is farther away, the spacecraft would need to travel longer or move faster, imposing even harsher demands on energy, heat management, navigation, and durability. The true distance is therefore not a minor detail. It may determine whether the entire concept remains within the realm of serious study or is pushed many centuries farther into the future. For that reason, the first step is not to build the laser array or manufacture the sail. Humanity must find the nearest black hole and determine its mass, spin, direction of motion, and distance with sufficient precision. The object would need to be monitored for years to predict its future trajectory and evaluate whether its surrounding environment was suitable for the intended measurements. Only when the target became clear could we ask how much energy the journey would require, how long it would last, and whether its scientific value would justify the effort. That black hole may already lie within a region of sky we have observed many times. It would not shine like a star, appear as a clearly defined black point, or announce its location with a brilliant ring of heated gas. If it exists in isolation, its only traces might be the slight displacement of a background star, light bending briefly out of its expected path, or the orbit of a nearby object changing in a way that is difficult to detect. Finding it may require many more years of data, more precise telescopes, and the patience to follow variations that are almost invisible. When that day arrives, the question will no longer be only where the nearest black hole is located. Humanity will have to decide whether to begin a journey whose designers are unlikely to live long enough to see the result. The engineers who launch the spacecraft may witness only the first few decades. The scientists who receive the final signal may not yet have been born when the sail first unfolded. Between them will stand an entire succession of generations responsible for preserving the equipment, the knowledge, and the commitment to keep listening. The journey to the nearest black hole would therefore test more than materials, lasers, and electronics. It would test humanity's ability to pursue a question for longer than a human lifetime. Such a mission may not begin with a countdown or a burst of light above a launch pad. It begins by looking patiently into the darkness between the stars, until we recognize that something invisible is bending the light and curving the space around it.